So, next thing up is the law of sines. Before we talk about that, let's talk about an oblique triangle. So basically, up until this point, we have done trigonometry with right triangles. Now we're going to do it with non-right triangles, which are just called oblique asymptote or oblique triangles. Excuse me. So an oblique triangle is just a triangle that does not contain a right angle, and that's it. So basically, we're just going to be talking about triangles that are not right triangles. So, first thing, the law of sines says that if the regular triangle ABC that we've always talked about, right, in the usual manner, so remember the regular triangle, we have alpha is across from A, beta is across from B, gamma is across from C, right? So this is the regular triangle. We know that the sine of alpha divided by A is the same as the sine of beta divided by B, which is the same as the sine of gamma divided by C. So you can go ahead and on that handout for chapter 7, have all the formulas down. You can write that one down with it. So let's try some examples. So solve triangle ABC given all of these parameters. So we got to make our triangle. So 48 degrees is going to be alpha. Across from that should be A. 57 degrees is going to be gamma. Across from that should be C. And 47 is going to be our beta, which means across from that is B. So if we notice, right, we need to figure out, or sorry, not B, beta. Across from it is beta. So we need to figure out what is A, what is C, what is beta. All right. Well, beta is going to be the easiest one to find, right? Beta is just going to be 180 minus the two other degrees. So if we just plug that into our calculator, we should see that that is 75. So beta is 75 degrees. All right. And now we can just use law of sines. So now that we know that beta is 75 degrees, right? We see that across from it we have 47, right? So we can use either right now. So let's just do sine of 75 degrees over 47, right? That's beta and B equals, let's look at try to find A. So sine of 48 degrees over A, right? So 48 is alpha, so that's across from A. So this ratio should work out. Let's make some extra room. We're probably going to need it. There we go. All right. How do you solve for A? Well, you can multiply, right? So A times sine of 75 degrees over 47 equals sine of 48 degrees. If you want to do it individually, right, we can see that we can just multiply everything by 47. So A times sine of 75 degrees is 47 sine of 48, and then divide by sine. So A is going to be 47 sine of 48 degrees divided by sine of 75. And when we plug that into our calculator, we see that A is going to be about 36.2. And last, just got to find C. So if you notice, C is going to be the exact same thing, right? We're going to use it in the exact same way that we had just found A. So we do sine of 75 degrees over B, which was 47, equals sine of 57 degrees over C. So if we multiply, right, or we can, another way to do this, we could cross multiply, right? So C times sine of 75 degrees is 47 times sine of 57 degrees. Divide by sine. of 75 degrees. So that's what we get for C, right? So when we divide that out, we should see that C is going to be about 40.8. And again, if you don't get this when you type into the calculator, you might be in radians. So just make sure that you switch the mode over to degrees. Good. So 40.8. And that's our answer. Sweet. All right, let's look at another one. So let's solve this triangle. Remember, solving means finding all the other sides and angles, all the missing sides and angles. So if we have alpha is 47 degrees, then A, which is 100, will be right across from it. If we have C of 125, we know gamma is right across from that. Then last we get is beta and B. So we need to figure out what is gamma, what is beta, what is B. All right. So this time we have two angles, so that's not very helpful. We can't just subtract from 100 or 180 yet. So what can we do? So far, all we can do is law of sine, so hopefully that's going to work. Law of sines is always across from each other, right? So sine of alpha and A. So what's another thing that we know across from it? So we could try to do the beta and B, but then we end up with two different variables. That doesn't help us. So let's do the gamma one. That would make more sense, right? So we get sine of 67 degrees over 100 equals sine of gamma over 125. All right. So cross multiply, or actually this time we just need to simplify this side, right? So we can just multiply both sides by 125. So sine of gamma is 125. Sine of 67 degrees divided by 100. All right. So if we notice, this is about 1.15, right? So we know mostly that this is positive. So if you think about it, right, if we have sine of gamma equals 1.15, right? Well, if it's positive, how are we going to do this? Well, it's not 1, it's not -1, not 0, so we have to do it using the triangles, right? So the question we ask ourselves is, which quadrant is this in? And it's always 2, right? You're going to forget, but it's 2. And this is super important because if you mess that up and there is 2 different options, you might be missing half the problems. That's half the points off. That's not great, right? Good. So sine, when we think of sine, we think of y. So that's going to be positive in the first quadrant and the second quadrant. So sine, right, we got 1.15 and 1, right? 1.15 and 1 because it's over 1. So we can do, right, now that we know how to do inverse trig, we also know the other way to do that is that gamma is the inverse sine of 1.15. So when we type that into the calculator, inverse sine of 1.15, we end up with a domain error. Now, why is that? Why would we end up with a domain error? Well, if you notice, right, we still have right triangles in this case, because that's how we solve for angles. And in a right triangle, what side should be the longest? The hypotenuse. But the opposite is the longest. So this triangle doesn't make any sense, right? That's why we get a domain error. So this answer is just no solution to this. And we're done, because there's no way to do this triangle. There's no way to make this triangle with those parameters. So there's no solution. All right, let's look at another one. Well, those are not right. So we're just going to cross that out. And we'll say solve triangle ABC given A is 12.4, B is 8.7, and beta is 36.7 degrees. So look at our triangle. We have A across from alpha. we have B across from beta, which is 36.7, and then we have gamma and C. So this is going to start off the exact same way the last one did, right? So we do have beta and B, so that's going to be the sine 36.7 over 8.7. And that's going to equal, so we can see alpha is going to be the 1 since that's the only one with a 1 variable instead of 2. So sine of alpha over 12.4. So if we solve for alpha, we get that alpha, or sine of alpha, is 12.4 times sine of 36.7 over 8.7. And we can divide this out and see that that's a positive number. So how do we solve for alpha? Same as always, we do our triangles, right? So there's going to be one in quadrant 1, and there'll be one angle in quadrant 2. And we have to look at both of them. If you don't look at both of them, you're going to have the wrong answer. Both answers are correct. Going through this process is the way to do it. Don't skip this process. You need 2 different answers. So if we have, and this is why, because if we do, right, switch it around, sine of alpha is the inverse sine of 12.4 sine of 36.7 over 8.7, right? We end up with alpha is 58.4, about. That's what it's going to give us, right? And that's the only number the calculator gives you, which is why we can't always rely on a calculator, because we just said how many angles do we have? Not 1, we have 2 angles. Super, super important. So make sure that you have 2 angles here. So this is just the one in quadrant 1. So then how do you get the one in quadrant 2? This is the reflexive angle right there, right? So then how do you get the actual angle? How do you get this whole angle from angle 2? Or quadrant 2, excuse me. Well, same thing. So remember, that's going to be 180 minus 58.4, right? That's how we do reflexive angles in the second quadrant. All this is coming back. You need to know everything from chapter 5 all the way to now, right? The beginning of our trig sections all the way to now. All of it's going to come back. And so when we do that, we see that alpha is 121.6 degrees. So we potentially have 2 different triangles. There are 2 different triangles that could work for these parameters. So we got to consider those. So triangle number 1 is going to have alpha to be about 58.4. Triangle number 2 is going to have alpha to be about 121.86, or 121.6, excuse me. All right. So if that's the case for triangle 1, let's look at triangle 1. That means gamma is going to be 180 minus the 58.4 minus what we had for beta, which was 36.7. So if that's the case, then we see that gamma is 84.9 degrees. Alternatively, if alpha is 121.6, gamma is 180 minus 121.6 minus 36.7, so it is 21.7 degrees. And then lastly, we just need to figure out what's left to figure out. So we already know what gamma is. We know what alpha is. So C is the last thing to figure out. And the way we're going to find C is just, once again, by using law of sines. So we get sine of 36.7 over 8.7, right? That's beta and B. And that equals sine of 84.9 degrees over C. If we multiply these out, rearrange them, we see that C is going to equal 8.7 sine of 84.9 degrees divided by sine of 36.7 degrees, which means that C is about 14.5. So this is one answer. But, and if this is all you give, right, you only gave half the problem. So you'd miss half the points, which is why it's super important that we have two answers, right? That we consider the second possibility. So in the second possibility, we have sine of 36.8 divided by, or 36.7 divided by 8.7 equals sine of 21.7 divided by C. So in the same way, you see that C is 8.7 times sine of 21.7 degrees over sine of 36.7. So when we plug all that into the calculator, we see that C is about 5.4. So this answer is going to have two different solutions. One for two different ways of configuring it. All right. So let's go to our word problem. So going to the word problems handout. When the angle of elevation of the sun is 64 degrees, the telephone pole is tilted at an angle of 9 degrees directly away from the sun. Cast the shadow 21 feet long on the ground. So approximate the length of the pole. So it might be good if we actually knew what this looked like, right? So we have an elevation of the sun. So elevation, here's the sun, right? And this has to be the angle of elevation, goes up. So a telephone pole is tilted at an angle of 9 degrees away from the sun. So here's the sun. If it's away from it, we can see this could be the angle, right? And if it's the angle directed away from the sun, it should be standing straight up, right? So that's where the 9 degrees comes into play. The shadow on the ground, right? So the shadow that's cast by this is 21 feet long. So what is the length of this pole? All right. So we're going to try to find the length of that pole. We need to know some stuff, right? So this triangle right here is probably the one we're going to be using, right? Since that's a side of the triangle. So we can see that we know what this angle is, right? So this angle should be 81 degrees. Because the whole thing from here is 90 degrees. So if you subtract that 9-degree slant, you get 81 degrees. Which would mean, of course, that this angle up here would be 35, right? We get 180 minus 81 minus 64, which is 35. All right. So we need to know what this length is, right? So we could call it X. Try to figure out what that length is. And now, so the reason why we need to know what this angle was is because this is the angle across from our 21, right? So that's how we use the law of sine, to know across from each other, the angle and the side across. So we can do sine of 35 degrees over 21 equals sine of 64 over x. Remember, this is what we're trying to find, and we already had this angle. So if we're going to use the law of sine, we need to know across from this 21, because that's the only other side that we knew. So we can see that x is going to be 21 sine of 64 degrees over sine of 35 degrees, which means that x is 32.9 feet. And that's it. So basically it's very similar to the one we just did, right? Well, we don't have to find all of them. And we have to know how to draw the graph. All right. Now let's talk about navigation. So navigation is the last way that we'll talk about for applications when it comes to trig. And I wanted to wait until this section because we need to talk about inverse before we had gotten to this point. So in a certain navigation or survey problems, right, the direction, also known as bearing or bearings, from point Q or P to point Q is specified by stating the acute angle that segment PQ makes with the north-south line. So, if we have, right, so it's north, south, east, west. If we have, so this is where, let's say, you're going from P, so this is where P is, and we're going to Q, right? The angle that we are creating, typically, right, when we do our standard positioning, we always go down, right? We're always going with the x-axis. However, with navigation, this is the only time that we are doing the north-south line. This is the angle that we have to use when it's talking about bearings. Essentially, the idea is we are always going north or south. We're just going east or west of that direction. So note, so we also state that whether Q is north or south and east or west of P. Yeah, so it doesn't matter which direction we have. So note that when this notation is used for bearings or directions, yeah, I guess we can just singular, north or south always appears to the left of the angle, and west or east appears to the right of the angle. So if we're actually drawing what this angle is, so let's say, here's an example, right? So this is 52 degrees. So what direction are we going if we're going from P to Q? We're going north, 52 degrees east, right? Northeast. That makes sense. So what if we're going in this direction? And we knew that this angle was 17 degrees. So that would be south, 17 degrees east. All right, what if we are going in this direction, 47 degrees? Well, some people might say we're going north 47 degrees west, but are we going north if this is the angle we're looking at? No, this angle is connected to the west, right? And we don't talk about west-north. That doesn't make any sense, right? So remember, if we're going in this direction, what angle do we always have to be touching? The angle needs to be touching the north-south line. Is this angle touching the north-south line? It is not. So this is not our angle that we're trying to find. This is the angle that we need for direction. This is the angle touching the north line. So the way we figure that out, right, of course, is 180 minus 47. Oh, not 180, excuse me, 90, right? Because these are all 90-degree angles. So 90 minus 47, and we get 43. So this is north, 43 degrees west. All right, and then real quick, last thing, because we're going to see this a couple of times. So let's just do an example. So we're going north, south, east, or west. So let's say that boat number 1 is going in this direction. Boat number 2 is going in this direction. We know that this angle is 27 degrees. You can write it in the black, 27 degrees. We know that this angle is 34 degrees. So the question is, in what direction is boat 1 going? In what direction is boat 1 going? So hopefully you know it is not 27 degrees, right? It's not, we're not using that 27 degrees, right? Why? Because it's not touching the north-south line. It's touching the west-east line. We don't care about west-east, right? So what we need to do is we need to figure out what angle does 1 make when it touches the north-south line. Now again, some of y'all might be thinking, oh, it's this angle, right? This is the only other angle. But is this touching north-south? No, it's not. So you have to go all the way from here to the north-south line. So it's both of this. It's the whole thing, right? So then how are we going to figure out what this whole angle is? Well, first we need to figure out what this angle is, this little one. And then we can just add those two together, right? So we know that the whole thing from here to here should all be 90 degrees. So we can do 90 degrees minus 27 degrees minus 34 degrees. And we end up with 29 degrees. So this little angle is 29 degrees. So if this is 29 degrees and this is 34 degrees, and the entire angle we're going, right? We can see the whole angle is 36 degrees, which means that we are going south 63 degrees west, right? So don't make another line make that confusing for you, right? You're always going from your direction to the north-south line. No matter how many lines you have to pass through that, you're going from there to the north-south line. That's super important. All right, so let's look at some more examples. So 2 ships leave port at the same time. 1 ship sailing in the direction of north 23 degrees east at a speed of 11 miles per hour. The second ship sailing in the direction of south 67 degrees east at 15 miles per hour. So approximate the bearing of the second ship from the first. So here's a trick when it comes to these types of problems. So let's put a pause on that. When it is asking for direction, if it is, so this is some strategy, a strategy for finding bearings or direction. So there are 2 things that you have to do to be able to do this. Probably. You have to use both of these things. You have to use inverse trig somehow. If you don't use inverse trig, you aren't doing it right. Another thing you have to use is alternating interior angles. That's also something you have to use. Now, what is alternating interior angles? So if we go back all the way back to geometry, remember, if you have 2 lines that are parallel and they are crossed by a line called a transversal. So not super important, but that's called a transversal line. There are lots of angles that are created because of these. And the ones that we need to look at specifically are the alternating. So they go on the opposite sides of the transversal. Interior, so that means they're inside these lines. So these would be examples of alternating interior angles. Also, these would be an example of alternating interior angles. And what we know about both of those angles is that they are the same. Mostly that they have the same measurements. So both of those concepts we need to use if we're trying to find what direction or bearings that we need to go. So again, if you don't use both of these, you haven't done it right. All right, so 2 ships leave port, same time. So we have our north-south line, and I would actually suggest not writing the east-west line. That's just going to mess you up. So let's put our direction. So this is where we start, and let's just do the north-south line. So 1 ship is sailing in the direction of north 23 degrees east. So north east is going to be in this direction, and this is 23 degrees. And this is 11 miles per hour. We'll talk about that in a second. All right, next, the next ship is going south 67 degrees east at 15 miles per hour. So first, which one should be longer? Which side should be longer? Well, this one's going faster than this ship, right? Maybe it should be the case that this one ends up going further. So for these problems, it might be good just to do a little exaggeration, right? So if one's supposed to be longer, just make it really longer. It'll help when it comes to the direction. Because basically, it depends on how far this goes. If this only goes this far, right, we're going to go in that direction. But if it goes a lot further, we're going in this direction. Those are 2 different directions, right? So yeah, it might just be good to try to over-exaggerate some lengths if we think we need to. All right, so the question is, approximate the bearings or the direction from the second ship, so that's this ship, to the first. It is super important that you know which ship you're going, what direction you're going. So maybe even make an arrow. All right. So this is what we got to do. So first step after you draw it, you need to make the north-south line. Right? So you make a new north-south line from your current direction. So we are currently, right, when the question is asking, approximate the bearings from the second to the first, this is where we're starting again. So we need to make another north-south line. Next, we need to identify our angle, right? What's the angle that's creating this direction? So remember, the angle is your direction to the north-south line, right? The direction you're going to the north-south line. So this is the angle that we need to get. And if you notice, this angle is not in our triangle, which is going to be different. So we'll try to figure out what that is in a second. All right. So remember, the two things we need to find, we need to use inverse trig, and we need to use alternating interior angles. So one thing we haven't written is how fast things have gone, right? That's not something we've written at all. So first, it tells us after 1 hour, right? So after 1 hour, if the first one is going 11 miles per hour, how far have they gone? Obviously, they have gone 11 miles. If the second one's gone 15 miles per hour, obviously, that's 15 miles, right? All right. So if we are looking at this, right, we can try to find inside. So inverse trig, right? Trig, you need triangles. So this is our triangle that we need, right? We have one side, we have another side, so we need some angles. So this angle is probably one that we need to figure out, right? So obviously that's going to be 180 minus 23 minus 67, right? Because that whole straight angle, we're taking away those two. So 180 minus 23 minus 67. 90. Oh, okay. This actually makes things a little easier on us. This is just a 90-degree angle. All right. So first, let's look at this alternating interior, right? So if you notice, where's our parallel lines? Parallel lines are always going to be the north-south lines. So the problem right now is that there are a couple of transversals. So which one is going to be the more important one? Well, first of all, it has to be connected to the north-south line, right? If it's not connected to this, it's not going to matter. So this little angle, we're not using an alternating interior for that, right? Because that's not touching the north-south line. So what angles currently are touching the north-south line? Well, we see this one, but as we said, we need both of these, so it's not going to be that easy, right? It can't just be alternating interior. We need both things to figure that out. So we see that these are the two angles that we are using, right? Well, does this line go all the way to the next one? No. So probably not going to use this one, right, for alternating interior. Does this angle, right? This angle is also touching. Is this line go all the way to the other one? Yeah, it does, right? So hopefully you can kind of see where we're going with this, right? So here are two parallel lines. Here's our transversal. And this, right, from this transversal to the line, that's going to be our 67 degrees. So from the transversal to the line, this whole thing is 67 degrees by our alternating interior angles, right? The whole thing is 67 degrees, which is good, right? So now, how can we figure out what this little angle is? Well, if we figured out what this little angle was, we could just subtract the two, right? This whole angle minus this little bit. And this is where the inverse trig comes into play, right? So actually in this case, we can see that since we have a right triangle, right? So right now we have 15 and we have 11 and we have this angle. So what's a trig function we could use with this? We actually see that we could use tangent, right? Tangent of this angle, let's call it alpha, super doesn't matter. So tangent of alpha is 11 over 15. So we see that that's positive. So to do our triangles, right, we need to do our triangles. When is tangent positive? It's in the first quadrant and the third quadrant. We need to talk about both of those, right? However, it's we also know that our angle alpha is a part of a triangle. Triangle can only go as big as 180 degrees. So it's never going to get past 180. So in this case, we only need to look at the first quadrant, but you do need to go through this process, right? All right, so alpha, right, if we rearrange it in the other form, it's going to be the inverse tangent of 11 over 15, which we see alpha is 36.6 degrees. So this little angle is 36.3 degrees, right? The big angle is 67, so if we kind of redrew it, right, we see that this whole thing is 67 degrees. This little bit is 36.6 degrees. Sorry, 36.3. So then how do we find that? We just subtract. So x is just 67 minus 36.3. So we see that it is 30.7 degrees. So what direction are we going? Well, we notice this is northwest. So we are going north 30.7 degrees west. Whew. Yeah, these are some of the most complicated things we'll do in this class. This might be the most complicated thing we do in this class, I think. Yeah, I think this is probably it. Might be the most complicated thing. But you can always start using these 3 steps, right? So let's definitely do some more. All right, so a point P on the ground is 3.0 kilometers due north of point Q. So let's already draw that. All right, so due north, 3 kilometers. So it's super important that we read these directions, right? A point P lies on ground level, is 3 kilometers due north of Q. So my question is, does that mean Q is above P, or is P above Q? Which way are we supposed to draw this? So hopefully if you read, it says point P is north of Q. So P is the one that's closer to the north, right? All right. So a runner proceeds in the direction from Q north 25 degrees east. So this is going to be 25 degrees. Oh, we can probably draw a little smaller. There we go. Then from north, from R to P, right? So this is R. South, 70 degrees west. Okay? Well, hold on a second. If we write like this, right? And we do a new line, because it's a new direction. If we go in this direction, isn't that north? But we need to go south. So this is when we talk about making some exaggerations. So if it's below this point, we're going to have to be going south. So it needs to go as far to start going south, right? It needs to go past the point. So this direction. And so here's my question. Where's the 70 degrees coming into play? If you said this is 70 degrees, you are incorrect. Because remember, what do all angles have to be touching? All angles go from your direction to the north-south line, right? So this is your direction to the north-south line. This whole thing is 70 degrees. So now we need to approximate the run. How far did you run from Q to R and R to P? So probably going to be using some law of signs here. All right. So if this whole thing is 70, right? Well, the only thing we have right now is this 3 kilometers. So it might be good to know what some of these other angles are. So, I guess that's not, the whole thing is 70. There we go. All right. So we need to figure out what some of these angles are. So, 1, we already did, right? We already made our north-south line. 2, what was 2? Identify the angle. So, so luckily this isn't asking about direction, but it's still going to be using all these things. So this angle ultimately is what we need to find if we're going to use law of sines, right? Because that's the one across from it. So should probably be using maybe some inverse trig, maybe not, we'll see. But what are some things that we do know? Well, we can use alternating interior angles to find some angle. So what angle do we know with alternating interior angles? So remember, we need parallel lines. Here's our parallel line. Whoop. And we need an angle connected to the parallel line. So we do have this one, right? This whole thing is 70. We do see that this whole thing is 70. However, right, that would mean if we use this line as our transversal, that would mean on the opposite, alternating, this is 70 degrees. Is this one we want? No, that's not really part of our triangle, right? So that's not helpful. So what's another? There's just a little too many lines right now. There we go. So another transversal would be this one, right? And we see that this is 25 degrees. So then using alternating interior angles, what also would be 25 degrees? Not inside, right? Because this isn't right here. That's not touching our north-south line. It has to be touching our north-south line. So this is on the alternating interior. So that's this angle right here, the small one. This little angle is 25 degrees. Which means, what's this small angle going to be? Just the whole one, 70 minus 25, which is 45. So this little angle is 45 degrees. Now we can find these distances, right? Because we need to know what's the length of Q to R. We can call that X. And what's the length from R to P? We can call that Y. So right now, right, we can see that we have, this is across from each other, which is law of sines. We also know that the 25 is across from the Y. So now we can figure this out. So sine of 45 degrees over 3 equals sine of 25 degrees over Y. All right, so we can just see pretty easily that that means Y is 3 times sine of 25 degrees over sine of 45 degrees. Which means that Y is about 1.8. So 1.8 kilometers. So this distance right here is 1.8 kilometers. Now we need to figure out what X is. All right, so across from X, right, if we're going to use law of sines, which might be probably what we need because we don't have any right angles, that's going to be this angle. So we need to figure out what is that angle. Well, since we have a triangle, right, we have a triangle right here. We know that one of them is one angle is 25 degrees, one angle is 45 degrees. So we can do 180 minus 25 minus 45. And we end up with 110. So this angle is 110 degrees. And now we can do exactly the same thing we did, right? We got across. So that's going to be law of sines. So using the same method that we just did, let's give us some extra space. We can have sine of 45 degrees over 3, right? We have 45 across from the 3 is sine of 110 over x. So we can see that x would mean that it is equal to 3 times sine of 110 over sine of 45, which means x is about 4.0 kilometers. So this right here, 4.0 kilometers. So 1.8 plus 4.0, we get 5.8. So that's our final answer, 5.8 kilometers. And you may be asking yourself, wait a minute, we didn't use inverse trig, but remember that's only for when it's asking for direction or bearings. This asks for distance, so we didn't necessarily need to use inverse trig. That's only when it's asking for direction. So I'm actually going to add an extra problem because I think it's important that we understand this. This is probably the most confusing. So let's do another one like that. So I'm going to do 3.5. So we'll come back to that. Yeah, let's do problem 3.5. Okay, so let's say 2 ships. Oh, we'll even go a little harder. So 1 ship leaves port at noon in the direction, let's see, north 37 degrees west at 20 miles per hour. Second ship leaves the same port at 1 o'clock in the direction of north 45 degrees east at we'll say 17 miles per hour. So in what direction must the first ship go to reach the second? Starting at 5 o'clock. So 1 ship leaves port at noon in the direction of north 37 degrees west at 20 miles per hour. The second ship leaves the same port at 1 o'clock. And we'll say it's 1 p.m. in the direction of north 45 degrees east at 17 miles per hour. So in what direction must the first ship go to reach the second ship if we start starting at 5 p.m.? So at 5 p.m., both of the 2 ships stop. What direction does the first ship have to go to reach the second ship? All right, so drawing this is going to be helpful. There we go. All right, so yeah, we need definitely a lot more space. There we go. So first ship. So here's port. The first ship leaves north 37 degrees west at 20 miles per hour. So 37 degrees, 20 miles per hour. So how far does this person end up going? They start at noon. They end at 5. So it's 5 times 20 miles per hour, right? 20 miles per hour times 5, 100 miles. Second ship starts going in the direction of north 45 degrees east. And they go in that direction for how long? So they start at 1 o'clock. We're ending at 5 o'clock, so that's 4 hours. So 17 miles an hour times 4 hours, we get 68 miles. So since that's shorter, right, we can be a little exaggerated, go a little shorter with it. So the question is, if the first ship tries to hit the second one, what direction do we need to go? So this is our direction. Here's our first ship. We're going in that direction. Maybe putting arrows might be helpful to remember what direction you're going. So remember, step 1, north-south line. So from our new direction, we need to make our north-south line. So that's this one right here, right? North-south line. Step 2, what's the angle that we need? So the angle for the direction, right, needs to go from your north-south line to the direction that you're going. So if this is our direction, and this is the north-south line, right, then we need this big angle right here. This is what we're trying to find. And then lastly, we know that we need inverse trig somehow, and we need alternating interior angles. So alternating interior angles probably going to be the easiest ones. So if these are our two parallel sides, what could be helpful to try to figure out using this giant angle to try using alternating interior angles? Well, we can see, right, that from this line, this little angle of 37 degrees is touching this transversal and this parallel line. So if we're looking at the transversal, right, oh, that was a little too wide. If we're looking at our transversal, right, what's on the other side of this angle? We see it's this angle, right? This angle is across from it. And then we're done, right? Hopefully you all said no, right? Because we need the big angle. So this is just a little angle. We need the whole thing. So we're on our way there, right? Now we just need to figure out what is this little angle, right? And then we can figure it out. And that's where inverse trig comes into play, right? Inverse trig is going to be with the triangle. So here's our big triangle. All right. Oh, we also know that this was 68, we said, I think. Yeah, this was 68 degrees, or 68 miles, excuse me. Good. So we know that this whole angle right here, if we add that up, 37 plus 45, we end up with 82 degrees. So this angle right here, if you want to rewrite it, this is 82 degrees. All right. So we can see that this angle is also 45 degrees, right? From alternating interior angles. Of course, that doesn't really help us. So we're going to have to use inverse trig somehow. Probably going to have to use law of sines somehow. So right now, right? Let's see. Right now, oh, that was the problem, I think. Yeah. Sorry. That's not supposed to be 82. That's supposed to be a different angle. So we're just going to change the angle. I know what the problem was. That was my bad. So we're going to make this angle 53 instead. So my bad. We're going to make that 53. So nothing changes, just that angle right here of 53 degrees. Yeah. So this is why we need this to be 53 degrees, right? Because this total needs to be a right angle. And the reason why we need that is because we have this right angle, right? But we didn't have what was across from it for a law of sines. And there was no way to figure this out given that this was 82 degrees. So we actually need to know that this is a 90-degree angle to do this problem, as far as we know. In the future, we'll be able to do problems like this, but for right now, we needed to know what angle was across from it, or what the side was across from it, and there was no way to figure that out if it's not a right triangle. All right. Now that it's a right triangle, we still don't have to figure that out, right? Because we see that if this is the little angle that we need to find, we can call this alpha, right? Across from it, we have 68 miles. Adjacent to it, we have 100 miles. So we know tangent of that alpha is 68 over 100. So if we're going to do inverse trig, right? And if it's not 0, 1, or -1, we have to do triangles. So when we do triangles, we have to ask ourselves, what quadrants is it in? It's always 2. If you have one answer, you are wrong. It is always 2. This is positive. When's tangent positive? It's in the first quadrant and the third quadrant. However, we've already talked about right now, right? Since it's a part of a triangle, it can't be in the third quadrant. So in this case, it ended up being okay that it was just 1. In the future, right, we've already seen examples where 1 is not okay. So we need to keep those into consideration. All right. So we need to figure out what is this actual angle. So we can turn it into our other form, right, using inverse trig. So alpha is inverse tan of 68 divided by 100. So we see that alpha is about 34.2 degrees. Right? So this little angle is 34.2 degrees. This little angle is 37 degrees. So all we got to do is just add them together and to get our big angle, right? So when we add these together with the 37 degrees, we end up with 71.2 degrees. So what direction are we going? So this is our angle. So we can definitely see we're going southeast, right? So final answer, south, 71.2 degrees east. So this might take some time getting used to it. But these are definitely 3 steps, the first 3 steps that you can do for these types of problems when it's asking you to find your direction or bearings. All right, let's look at the last problem, and then we'll call it a day for this lesson. A commercial fishing boat uses sonar equipment to detect a school of fish 2 miles east of the boat, traveling in the direction of north 51 degrees west at a rate of 8 miles per hour. If the boat travels 20 miles per hour, approximate to the nearest 1 degree, the direction it should head to intercept the school of fish. All right. So we know that, let's see, it says 2 miles east. So directly east. So the question, again, right, is this where the boat is and this where the fish is, or is this where the boat is and this where the fish is? So reading our directions, the boat detects school of fish east of the boat. So the fish is 2 miles east of the boat. So this is the way it's going to look, right? Fish is on this side, 2 miles. And that does matter. All right, so the fish is 2 miles east and traveling in the direction of north 51 degrees west at 8 miles per hour. So this is the direction that it's traveling, and this is where the 51 degrees is, right? Hopefully you said no. Why is that not where the 51 goes? Because that's west-north, right? Remember, the direction is always north-south. This is our 51 degrees west. It's going 8 miles per hour. So if the boat travels at 20 miles per hour, in what direction does it need to head? So assuming it's going in this direction, right? It needs to intercept it at some point. What direction does it need to go? So step 1 for the direction problems, north-south line, right? Make your north-south line. Here it is. We're starting at the boat. We need to head in that direction. Number 2, what angle do we need? The angle is from your direction to the north-south line. So here's our direction. Here's the north-south line. This is what we need to find right there. All right. And then 3, probably going to need to use alternating interior. Probably going to need to use some inverse trig, maybe. So, let's see. So one thing that we might need to know. So here is 51 degrees, right? So inside this angle, we should see that that's going to be 90 minus 51 degrees, which is 39 degrees, right? So inside, here we get 39 degrees. Okay? So if we knew what this angle was, we could figure out where that is, right? If we knew what this angle was, we could figure out what this is. So we might need, we don't see any right angles in here. So since there's no right angles, we're going to have to use law of sines. So for the law of sines, right, we need across. So what's across from this one? Well, this one's going 20 miles per hour. So then how far are they going? So they didn't tell us how long it took, right? We're going to have to figure that out later. So let's think about this. If it was 1 mile, or 1 hour, how far would the boat be going at 20 miles per hour? Obviously 20 miles. If it was 2 hours, how much would he be going? Hopefully we said 40, right? Because that's 2 times 20. What if it was 3 hours? It'd be 60, right? 3 times 20, which is 60. So if we don't know how many hours, let's say it's x hours, then how far are they going? Well, if we're using our pattern, it should be 20x miles, right? So this is just 20x. In a similar way, right? The fish, if they're going in 80 miles per hour, this distance is just going to be 8x. So now we can see that we can use this across with the 20x, this across with the 8x. We can figure out what this little distance is. We can call this alpha, right? This little angle. So let's give us, once again, give us a little more space. All right. So using law of sines, we can see sine of 39 degrees over, what's it across from? It's across from the 20x equals sine of alpha over, what's it across from? 8x. So we're trying to solve for alpha, sine of alpha, right? Get that by itself. We can multiply by 8x. So sine of alpha is 8x times sine of 39 degrees over 20x. And looky there, x's cancel, so we need to worry about that. So we see that sine of alpha is 8 sine of 39 degrees over 20. And you can easily divide that out and see that this is positive. So how do you find it? It's not 1, 0, or negative 1. So we need to do our triangles. So what's the first question you ask for the triangles? Which quadrants is it in? And we know that this is going to be in the first quadrant and the second quadrant because it's y, right? When we think of sine, we think of the y values. So we need 2 answers here. So when we plug it back into our other form, right? we get that sine, or alpha, is the inverse sine of 8 sine of 39 degrees over 20. So if we plug that into our calculator, we see that alpha is going to equal 14.6 degrees. However, that is just for the first quadrant, right? This little angle is 14.6, which means the other reflexive angle is 14.6. What the calculator doesn't tell you is what's in the second quadrant. So how do we figure out what's in the second quadrant? We can do 180 minus 14.6 degrees, which is 165.4 degrees, right? That's this whole angle right here that we're trying to find. All right, so we got two different angles now. Oh no. So if we draw, if we look back at our triangle, right? So if this was the second one, right? 165.4, and this was 39. Does this triangle make any sense? It actually doesn't, right? 165.4 plus 39 if you plug that into the calculator, see it's definitely over 180 because it's 204.4. So can this triangle happen? No, it can't. So actually this time we are only in the first quadrant. But as you already saw, right, from that previous example, sometimes you do end up with two different angles, two different triangles. But luckily, in this case, it's just the one, the 14.6. That's the only one we have to worry about. All right, so going back here, this is 14.6 degrees. So how do we figure out what this angle is? 90 minus that, right? So when we do 90 minus that, we end up with 75.4 degrees. So what direction are we going? North, 75.4 degrees east. Good. Part B. To the nearest minute. Find the time it would take the boat to reach the fish. So we just draw it again real quick. So this was 20x, 8x. We said this was not 39. 14.6. This was 39 degrees, right? And this was 2 miles. So how long will it take them to reach that boat? So basically what we're trying to find is what's x in minutes? Because we already said x was the hours it took, right? Okay, well, basically we need to isolate x. So we can't do what we already did, right? Because remember when we did it this way, we just ended up canceling x, and that wasn't any help. So we need to know something with this actual 2. So what's across from the 2? It's this angle. So what is this angle? Oh, that's easy. We can just do 180 minus the other 2. 39, 14.6. All right, and we end up with, when we subtract those out, 126.4 degrees. So this is 126.4 degrees. So using law of sines, we get sine of 126.4 degrees over 2 is, and we can really do any of them, but if we're trying to be more exact, we should use the most exact answer, which is the 39. Sine of 39 degrees over 20x. And they're just trying to solve for x, right? So we can see that this simplifies down to x equals 2 sine of 39 degrees over 20 sine of 126.4 degrees. So then when you divide that out, you end up with 0.07818 hours, right? But we need it in minutes. So then there's a minute. So then we just multiply this by 60. And we multiply by 60, we get 5 minutes, right? Because we get 4.69. So nearest minute would be 5 minutes. All right. I know this was really difficult, so please, if you have any questions, make sure to email me, contact me, text me, whatever you need to do. We need to make sure that you understand this. But other than that, we are done. So y'all have a great day.